Now we're going to continue by coding our algorithm into Python, and we will extend this algorithm and we will test it to make sure that it will work for all quadrants in all circumstances. So that's the route we're going to take moving forward. So I've rewritten the algorithm here and I've coded this basic algorithm into Python. So we're going to have the variables x1, y1, x2 and y2, and you're going to input them as integers. Then we have to work out the initial decision algorithm, initial decision variable. So it's going to be p1 is equal to 2 delta y minus delta x. So we have to work out the delta y and the delta x. So we'll call the delta x dx. So it's going to be x2 minus x1. The delta y we'll call dy, and that's y2 minus y1. Then we're going to have to work out the initial decision variable p, and it's going to be 2 dy minus dx. So p is equal to 2 times dy minus dx. And then we're going to have to work through a loop, because we're going to start off with the first x value, and then we're going to have to work out the position, so the y value, and then we're going to have to move it on to the next one and again work out the y value and move it on and work out the y value, and we will continually do that until the value x1 goes all the way along to the value x2. So we could write while x1 is less than or equal to x2, then we can go through the rest of the loop. So first of all, what we're going to do is we'll print the values of our outputs, so x1 and y1. So this little line here will allow us to print those values out. Now, irrespective of whether the value p is less than 0 or greater than or equal to 0, we're always going to be incrementing the value of xk by 1. So we're going to have the x1 value, and it's going to be plus equals 1, so it's just adding 1 on each time. And then we're going to get into the actual little bit of the algorithm here. So we're going to have an if statement. So if p is less than 0, we want to do this. So we're going to have p is equal to p plus 2 dy. So we've got it written here, p equals p plus 2 times dy. Now, if that's not true, it goes to the else. We're going to have the value's got to be greater than or equal to, in which case we go through this part of the algorithm. So we'll have p plus 2 dy minus 2 dx. So we've got p plus 2 times dy minus 2 times dx. Now in this instance here, whenever the value is greater than or equal to 0, the value for y gets incremented. So we've got y1 plus equals 1. Now the value for y doesn't get incremented in at this section here, because y remains the same whenever the value for pk is less than 0. So that's our basic little algorithm all coded in. So what we'll do is we'll run this and we'll pick out some values. So let's say we run from 1, 1 to 8, 5, and there you see here it's going to generate the values 1, 1, 2, 2, 3, 2, 4, 3, and so on and so forth. Now, I have checked these values and they are actually the correct values. So it does work, but of course this is only going to work under limited circumstances. So it's not going to work whenever the gradient is greater than 1. Also, another thing, it won't work. It won't work if we decide to swap these values round about. So if we were to, say for example, put in what is in fact the same line, so but we start at the other end. So we start at this end here and we go 8, 5, 1, 1. It won't give us anything. Okay, the algorithm won't work in that instance. We'll have to adjust the algorithm so that it will work both ways. But we'll get to that in a little while. That's just the first start of the algorithm, and it's a nice and easy little start. So how are we going to get it working both ways? That is, if we put in the value 1, 1 and 8, 5, we want it to draw the line. But if we put the value 8, 5 and 1, 1, we also want it to draw the line. So it has to be able to draw the line from one point to the other and from that point back. Now, the first thing to note here is that the dx and dy, we always want those to be positive values. In effect, it represents a length, and a length can only have a positive value. Now, we can get this quite simply by using the absolute value of x2 minus x1 and the absolute value of y2 minus y1. So that's the first change. And you can see this quite simply. If we had a point 8 and then the point 5, you could say 8 minus 5 is 3. You could also say 5 minus 8 is minus 3. So whether the answer is minus 3 or plus 3 doesn't matter. We know the length is 3. So we just have to change the minus 3 into a plus 3. We do that by the absolute value. Now that's the first thing that has to change. Another thing to note here is that the x increment previously was running 1, 2, 3, 4, 5, 6. But the x increment may run 6, 5, 4, 3, 2, 1. It can run both ways now. So we define this other variable called x increment, and it's going to be a value of plus 1 if x1 is less than x2. So that's the original setup that we had. But if x2 is less than x1, then we count the opposite direction. That is, we count in terms of minus ones. So we will be counting down instead of counting up. Now another thing to note here is that the while loop I had less than or equals to. But now it's no longer less than or equals to because we could be counting down or counting up. So what we can do is we can just put that as does not equal. Now when we come down here and we decide that we're going to increment the value for x1, so we could be incrementing it or decrementing it. So that's going to be covered by that x underscore increment, which we have defined up here. Now we'll go through the values for our decision variables. So the first part remains the same. Now in the second part here, we're going to be incrementing xy. But in this instance now, we can not only just increment xy, we may be decrementing it. So if we're moving in from left to right, then we will be incrementing. But if we move from the left to right, the right to left, sorry, then we will be working back the other way and we will be decrementing it. So we can say that y1 is going to be increment by a value of 1 if y2 is less than y1, which was the original situation. But now we've got the option of the value of y2 being less than y1, in which case we will then decrement the value. So this is a little bit of code here. Now let's just run it and we'll see it working. So we'll put in 1, 1, 8, 5, and you'll notice it's actually missing a value. It's missing the final value, which is 8, 5, which we'll deal with in just a minute. So let's run this again, and we'll run it round the other way. So we'll run it from the 8, 5, 1, 1. Now you can see here it's missing the first value, 1, 1. Now we can sort that out quite simply by adding the other print statement in. So we can print it out here. In this instance here, it will print the first the last points of x2 and y2. So if I run that, we'll see this now working completely. So we'll put in 1, 1, 8, 5, and now we've got all of the values. and then we can run it once more, and we'll put in the values 8, 5, 1, 1, and it's created all of the values. So you can see here that we've generated this for values for x2 can be greater than or less than x1. So that's the first thing that we want to do in order to extend the algorithm. Now, we want to be able to extend the algorithm also to values of the gradient which are going to be greater than 1 or less than -1. So let's see how we're going to do that now. I have an example here of using the Bresenham's algorithm for gradients greater than 1. Now you can see here we have the blue line and we have the grayed out blocks, which are the blocks which the Bresenham algorithm chooses, and we have the individual points that are generated within the algorithm. Now, whenever we used gradients which were less than 1, then we moved along the x-axis and then we made a choice in the y-axis. But now what we're going to do is we're going to move along the y-axis and make a choice in the x-axis. So for example, we take the first block here, which is this one, and we'll choose between this one and this one. And again, we take the next block here, which is this one, and we choose between this one and this one. And then we take the next block and we make a choice, and this time the choice is between this one and this one, and we've made this choice here and it goes to here. And again, we continue here moving up the y-axis and make a choice between this block and the next block, this one and this one, this and this, and we continue doing this until we come up to this point here and we make a choice between this block here and the next x block. So all we're doing is we're working up the y-axis and then making a choice of the x values, as opposed to when the gradient is less than 1, we work along the x-axis and make a choice on the y values. Now, the same thing applies as well whenever you're going from this end of the line down to this end. The only difference is that rather than increasing the value of y, we're decreasing the value of y. And then rather than working where we choose this one block and this block and this block, we're working through in the opposite direction. So when we come down the way, we're choosing between this block here and this one and this one, and so on and so forth. So it's just very similar to what we worked out whenever we did the gradients less than 1. So let's have a little look at the algorithm that does this. So here is the algorithm that will work for gradients that are greater than 1 and less than -1. So you can see here that the first part of it is exactly the same, entering in the values, working out the dx and the dy value, working out the initial value for p. But now what we're going to do is we're going to either increment the y value, or we're going to decrement the y value, depending on whether the value of y1 is greater than or less than y2, the same as we did with the values where the gradient is less than 1. And also whenever we come down here, we're doing the test, and it will end whenever y1 is equal to y2. And the value here, y1, will either be incremented or decremented. And when we come down to the bottom here, whenever we work out our values for p, if the value for p is greater than or equal to 0, then we're going to increase the value or decrease the value of x. So it's just the same type of code that we've seen in the previous example. In fact, I'll bring them up together so we can see them, one sitting next to the other. So you can see here the code on the right hand side works for gradients which are greater than 0 and less than 1. And the one on the left works for gradients that are greater than 1 and less than -1. And you can see the similarities between them. Now what we have to do is take these two pieces of code and join them together in some way so that we have a final Bresenham's algorithm which will draw all lines for all gradients. So let's do that next. So here is the final Bresenham's algorithm for all gradients. Now there's lots of different ways you can code this in, and if you find a way that you think is easier for you, then by all means go ahead and code it in your own method. So in this instance here, we're going to have a function. It's going to be called Bresenham underscore line, and it's going to have 4 variables. So we're going to pass these into the function, and the function is defined up here as Bresenham underscore line. Now the first little bit's the same. We're going to work out our dx and our dy, which is the absolute value over x2 minus x1 and y2 minus y1. Now first thing we're going to do is work out whether the gradient is going to be greater than 1 or less than -1. So in order to do that, we check the value for dy and the value for dx. So if the value for dy is going to be greater than the value for dx, then it means that the gradient is going to be greater than 1. But we're going to have to check it, obviously, whenever we're going in all different directions. So we're going to have to take the absolute value of the dy and dx. So this defines whether the gradient is greater than 1 or less than -1. So it's a steep gradient, so we'll call that steep. Now what we're going to do is we're going to take all of the possibilities of how we draw a line, and we're going to in effect just map them back into our first quadrant. So whenever we started off looking at Bresenham's algorithm, we looked at the xy coordinates and we imagined that it was a gradient which sat within the first quadrant. Okay, so we're going to in effect map everything into that first quadrant, work out the Bresenham's algorithm, and then unmap the values back out again. So if it is steep, then what we're going to do is we're going to take the value of our x1 and y1 and we're going to swap them round about. So the x1 becomes the y1 and the y1 becomes the x1. So this is equivalent to taking our graph, and instead of working along in the x direction and then changing the y value, the steep, if it was a gradient greater than 1, then we would work a lot up the y axis and then change the x values. But what we can do is we can in effect just swap the axes over. Okay, so if we swap the axes over, then in effect we're mapping that possibility into the first quadrant. And we could do the same for our x2, y2 and our dx and dy. Now the other thing we're going to look at is whether the x1 value is greater or less than the x2 value. So in this instance here, we're talking about whether we start at one end of the line and work our way back, or we start at this end of the line and work towards the point. So we're either working along the line in this direction or back up in that direction. Okay, and again what we do is we just map it. So if x1 is greater than x2, then we just swap them round about. Okay, so x1 becomes x2 and x2 becomes x1, and the same with the y ones. Now, if the value for our y1 is less than y2, then we can define the step as +1, and if otherwise it's going to be a step of -1. So again, we've gone into the first quadrant and we're assuming that we're counting along in the x direction, and either we increase the value of y by 1 or we're going to decrease the value of y by 1, depending on whether the y1 value is greater than or less than the y2. Now, we work out the value for our initial p exactly the same as we did previously. And then we run through, in this case, a little for next loop. So we're going to run from the point x1 up to the point x2. But if you remember, whenever we've seen in the previous examples, we were always missing out the last value. So we can catch that last value if we make it x2 plus 1. And once we've worked out the values for our Bresenham's algorithm, we can print them off. But again, whenever we print them off, in effect, we unmap everything. So everything up here for the if statements here maps everything into the first quadrant. And then whenever we put the final output, we unmap everything back out again. So in this case here, if it's steep, then the value for our x will be the actual y value, and the value for our y will be the x value. If it's not steep, then the x and y just remain the same. And again, we go through the actual Bresenham's algorithm here, which just remains the same. So if p is less than 0, then we get p plus 2 times dy. If it's greater than or equal to 0, we get our p plus 2 times dy minus 2 times dx. And then we increase the value for the y. Okay, so it either gets increased by a +1 or -1. And again, we print off here. If it's steep, we print off the value. The x value is the y value and the y value is the x value. If it isn't steep, then the x value remains the x value and the y value remains the y value. And we've got here where we actually been asked to input the coordinates. So it's a bit awkward to describe, and maybe the best thing to do is to work through a few examples, and you could maybe step through the program and you can see the program working. Or there are other methods of writing this out, and if maybe the other methods you might find easier to understand. But that's the Bresenham's algorithm that I'm going to stick with for the moment, and I'm going to try and code this Bresenham's algorithm into our assembly language and try and get it working on our machine. So that's us finished with this finally. I've done this to death now. We should know everything we need to know about the Bresenham's algorithm. So thank you for listening. I'll get you on the next video. Goodbye.